Let's start with relational databases. These are the most traditional and widely used databases, where data is stored in tables with rows and columns. They enforce a fixed schema and strong relationships between data, which makes them predictable and reliable. Relational databases support transactions, meaning multiple operations either succeed together or fail together, which is critical for correctness. This makes them ideal for use cases like user accounts, orders, inventory, and financial transactions. Because of these guarantees, banks, enterprise systems, and core business applications rely heavily on them. In interviews, relational databases usually represent correctness, structure, data integrity, and strong consistency guarantees. Next are in-memory databases. Unlike traditional databases that store data on disk, in-memory databases keep data in RAM, which makes read and write operations extremely fast. They are commonly used for caching frequently accessed data, managing user sessions, maintaining leaderboards, and powering real-time analytics. In-memory databases are often placed in front of slower databases to reduce load and improve response times. When you see an application responding instantly, chances are an in-memory database is involved behind the scenes. The trade-off is that memory is expensive, and without persistence or backups, data can be lost during crashes or restarts. Key-value databases are one of the simplest and fastest database types. Data is stored as a key and its associated value, similar to a dictionary or hash map. This design makes lookups extremely efficient and easy to scale horizontally. Key-value stores are widely used for caching, feature flags, user sessions, shopping carts, and quick lookups where complex queries are not required. They usually sacrifice advanced querying capabilities in favor of speed and simplicity. In interviews, key-value databases are often associated with performance, scalability, and low-latency access patterns. Document databases store data as flexible documents, usually in formats like JSON. Unlike relational databases, they do not require a fixed schema, which allows different records to have different structures. This makes them ideal when data models evolve frequently, or when requirements are unclear at the beginning. Document databases are commonly used in content management systems, product catalogs, configuration storage, and user profiles. They allow developers to move quickly without frequent schema migrations. Interviewers often expect you to mention document databases when flexibility, rapid development, and semi-structured data are important. Graph databases focus on relationships rather than just data itself. They store entities as nodes and relationships as edges, making it easy to traverse complex connections. This design is particularly powerful when relationships are deeply interconnected and queries involve multiple hops. Social networks, recommendation systems, fraud detection, identity graphs, and network analysis rely heavily on graph databases. They excel at answering questions like how two entities are connected or finding patterns across relationships. In interviews, graph databases signal complex relationship queries and traversal-heavy use cases. Wide column databases store data in rows and columns, but allow each row to have a different set of columns. They are designed for massive scale, high availability, and high write throughput across distributed systems. These databases are commonly used for logging platforms, analytics systems, time-based data storage, and event ingestion pipelines. They handle large volumes of data spread across many machines efficiently. When interview questions involve big data, horizontal scaling, or write-heavy workloads, wide-column databases often come into the picture. Time series databases are optimized for data that changes over time, with each data point stored alongside a timestamp. They are designed to efficiently handle continuous streams of data and time-based queries. Time series databases are commonly used for system monitoring, application metrics, IoT sensor data, stock prices, and performance tracking. They support features like data retention policies and downsampling to manage large volumes of historical data. In interviews, they usually appear when discussing monitoring, observability, or real-time analytics. Text search databases are designed to search through large volumes of text efficiently. Instead of relying on exact matches, they support full text search, ranking, relevance scoring, and fuzzy matching. These databases power search features in e-commerce platforms, document systems, content platforms, and log analysis tools. They are optimized for searching and indexing text rather than transactional workloads. When interviewers ask about building search functionality, autocomplete, or log querying, text search databases are the correct choice. Spatial databases store and query location-based data. They understand geographic coordinates, distances, shapes, and spatial relationships. These databases are used in navigation systems, ride-sharing apps, delivery platforms, real estate applications, and mapping services. Spatial databases allow efficient queries like finding nearby locations, calculating distances, or checking whether a point lies within a region. In interviews, they usually appear when dealing with maps, proximity searches, or geographic constraints. Finally, blob storage is used to store large unstructured objects like images, videos, backups, documents, and media files. These systems are optimized for durability, scalability, and cost-effective storage rather than complex querying. Applications typically store metadata in a database and keep the actual binary data in blob storage. Blob storage plays a critical role in content platforms, backup systems, and data lakes. In system design interviews, blob storage represents scalable, reliable storage for large files without overloading traditional databases. When you put all these together, you realize there is no single best database. Each database type exists to solve a specific problem and optimize for specific trade-offs. Strong system design and strong interview answers come from choosing the right database for the right use case, rather than defaulting to familiar tools. Once you understand why these databases exist and where they fit, system design questions become much easier to reason about.